Okay, this is a standard published by the Public Works Department of Malaysia pertaining to geometric designs of road, and it's a reference that we will normally refer to when we design roads. I will refer it as JKR ATJ. Okay, so that's the how I'm going to refer this manual or this standard. And ATJ stands for Arahan Teknik Jalan. So basically, the values that we'll come up with when we do designs, we have to compare with the standard. And the standard will be is based more or less on international values, but has been some sort of adapted to suit Malaysian condition. Okay, that's one table from the standard table 4.3, just to show the minimum radius of a circular curve pertaining or with respect to speed. So as you go down the table, you could see the radius gets smaller. So the value E here is what they term as super elevation rate. We will discuss that later, but for now, we'll have in this standard anyway, two different categories, one for urban roads and one for roads in rural areas. Okay, so that's the standard that we refer to. One example in the standard anyway. Okay, so how do we go about setting out a circular curve? We've looked at what should I say, the formula, also the theory involved. We have also looked at the geometry of it. So how do we go about putting that or putting the design on the ground? Okay, so this process of setting out, basically what we're trying to do is going to put markers which represent the center line. Okay, the markers which present the center line of the road or the route that we have chosen, and we'll mark that at interval that we've decided beforehand, regular interval. Okay, normal values 20 meters, 25 meters, some to 30 meters. Okay, and can go as low as 10 meters. Okay, so the most common method that suitable or should I say easily to be employed will be the deflection angle method. So how does this method work? I think I've got a simple diagram after this slide, but anyway, it involves what we call calculating the deflection angle from a point that we have chosen to set it on. Okay, so normally we will set out the point from the tangent point. Okay, let's see how this is done. Okay, if you look at that figure there, if that is the curve going like that, so in the process of constructing the curve, okay, to get the alignment, to get the shape, so we have put markers. So these blue dots here represent markers that we set in the ground, the regular interval that we have decided, and the builders then can use these markers to guide them to construct the curve or the shape of the curve. So it's the center line. So remember that it's the center that we are marking. Okay, so that's just example I took from Google just to show you how intricate curves can be. So 3-layer, 4-layer, 4 levels, should I say? Okay, so it's quite a fair bit of work in there. And that's also another example, going across a river. Okay, a flyover going across a river in terms of a curve. And that's one there going across the highway. Okay, so that's we have a very curve with a very large radius. We have curve with a smaller radius, and so on. Okay, now let's see how we do in the field. So, assuming that we have two straights, okay, starting from T1, going to the intersection point, and the next tangent point, T2. Okay, now we know that the curve will be somewhere along this line, okay, along here, and now we have to mark the points in the ground to represent the curve. So if the total station is marked at 1, we have set the total station at 1.1 here, tangent 1, okay, and let's say that's the first point. Okay, just go back one step. Sorry, go back one step. All right, and let's say that's the point that we have, the point that we want to put in. So we have to calculate the deflection angle. Then we measure out the distance, that distance there, and we mark the point. So that will be the first point on the curve. Then we will proceed with the next point, the next deflection angle, the next distance here, then we mark the point there. And we do the same thing for the rest of the point on the curve, so that we'll end up with that point there, using that deflection angle, and the point there, the second last point, using that deflection angle. Okay, and finally we're going to have one at T2. So when that is done, okay, we can now have points, what we terms have marked equal spacing, and the point represent, as I said earlier, the center line. Okay, and that will be the curve that we require. Okay, that's the curve that we require. So that's what we meant by using the deflection angle method. Okay, deflection angle and the distance, so that we could come up with the points that we want. Okay, putting it in the ground at regular interval. Okay, in the field it might look something like this. Okay, you have to put stakes in like that. Okay, stakes in, put it nicely firmly in the ground. Then you might have a few points along the line to present the curve. Okay, and normally it will be something like this. We'll have somebody at the total station instructing another person, putting the stake in left or right, forward or back, and so on. So that's a more or less scenario, okay, how it looks like, okay, when we're doing staking out or setting out a road curve. Okay, so that's how it's done in the field. And let's look now, how do we calculate the deflection angle? Okay, look at the, consider that that's the first tangent point, okay, that one point, and let's say that's the first point on the curve that we want to set up. So we need to find what that angle is, delta 1, and it's simply given by this. Delta 1 is basically, I'm going to work in degree now, it's basically TA, which is that's distance there, divide by 2r times 180 over pi. That's in degree. Okay. So for the next point, point B, we now need to calculate that deflection angle. So it's given by AB, which is that distance there, AB, over 2r times 180 over c. Sorry, over pi. Okay, so this little distance here, or TA, TB, that's what we call chord length. Okay, the reason I have separated the calculations is because sometimes, or most of the time, the first chord length may not necessarily equal to the second chord length. Okay, we will do one example later, and you see how, you see what I mean by that. Okay, but for now, the formula is quite straightforward. Okay, it's a ratio between the chord length and the radius, and twice the radius. Okay, now so when we're done, that'll be the curve that'll be fitting in, or be started anyway, going through the points that we have set out in the ground. Okay, let's do one example now. Okay, two straights meet at point I with a section point are to be connected by a 14-degree curve. The section angle is given as 21 degree. Calculate the setting out data at 20-meter intervals. Change of I is given as 2296.58. Okay, let's look what we have now. You're given a curve, okay, where the degree of curvature is mentioned, 14 degree. So there's no radius in here, which means that we need to calculate the radius. Okay, then we also know that theta is 21 degree, and we were told that interval is 20 meter, and change I is 2296.58. Okay, let's start doing this. Since radius not given, in fact only the degree of curvature is given, so we're going to convert that. So then I'm going to calculate R using the formula that I've just shown you. So then we're going to end up with about 409.256. Simply use that number now, put it in here to calculate the tangent length, okay, which is 75.851. So IT1 is equal to IT2. So if that is the straights, and let me just change color now. Let's put a yellow in there. And if that's a curve, okay, so T1 is here, T2 is there, then that's SI, so that distance there is equal to that distance, tangent length, okay? T1 as IT1 is equal to IT2. Length of curve, okay? I'll use green now. So this length here, here the curve length between T1 and T2 is given as R theta, and that will be 150 meters. Then the next thing to do is to calculate change T1. Change T1 will simply be that change minus that distance, will give you that. And change T2 will be that change plus the length of the circular curve, that will give you that change. Okay, once that's done, that's the initial data that we need. Then we can now prepare the table for the setting out data. Okay, so nothing complicated in there, quite straightforward. Okay, next slide. Okay, the table will look something like this. Okay, you're going to start with change 220.729. So that's your T1. So this is T1. So the next point after that, even though I said, even though the question says the interval is 20 meter, okay, but when we do the marking on the ground, we work with round numbers in the multiple of the interval. So if the interval is 20, so I'll have changes that ends with 40, 60, 80, 00, and so forth. If it says the interval is 10 meters, then I have changes ending with 10, 20, 30, 40, and 50, and so on. Okay, so the only time that we can have non-round numbers, okay, numbers which are not round, will be at the tangent point. So in this case, T1, not round, and the last one, tangent 2, is also not a round number because they are tangent points. We have to locate where they are. Apart from that, all other points should be round numbers in the multiple of the changes or interval, I mean. Okay, so let's look now. 2220729. So the next change or the next point, which is in the multiple of 20, will be 2240. We cannot have 2240.729. Okay, because that's not a round number. So the nearest one will be 2240. Then we will follow through 60, 80, 00. Till we get to the last point, we cannot go 2380 because it will be too much, too long. So we have to go the next tangent point, which is 2370, 7 to 9. Okay. So remember I was saying that the first chord distance in most cases will not equal to the next chord distance. The second one is simply because of this. Okay, because that's a round number, so you get a nice figure there. But between these two is okay, because T1 is not a round number, you will have a number which is less than the interval required. So if you look at this figure here, so you got 2220729. So that'll be the first chord, which is 19.271. 19.271. So the reflection angle for that will be 1 degree 20 minutes 56 seconds. Okay, will be that number there. Then the next point. Okay, I'm going to use a different color now so that we can differentiate. Yes, yellow will be nice. Okay. The next one. Sorry, my mistake. Got to erase that. Okay. The next one will be that chord distance, and we need to get that angle there. Okay. So that angle is 02. Okay, now again I'm very mistake. The angle there is 1.39999 degree. Okay, now we'll do the same. The same thing will happen at 2280 and so on. Okay, what I'm trying to highlight here is let me use this green here. To highlight now here is this angle, the first angle is between that tangent and that interval. Okay, whereas the second one, the angle there, that deflection is between the first chord, the first radial I mean, and the next radial. So that angle, okay, which is 1.39999, it's not referred to I. It's not referred from there. It's referred from the previous radial. So imagine that you're doing your work in the field. You might have your total station at T1 here, and you might set 0 degree to there. So for the first point, you just open up 1 2056, measure 19.271, you put in that point. But for the next point here, for point 2260, okay, the angle there is basically from this line. So which means that your 0 has to be there. Okay, I just draw a dotted line there. So your 0 would be there if you want to use 139,999. Okay, so it's going to be cumbersome. So what we're going to do is we're going to set 0 there. We're just going to add that angle, so that we just use 1 0. So that's why if you look at that column there, you're going to sum the deflection angle, so that when we get to the next point here, we just use the sum rather than using individual angle. So that's the reason why we have the last column there says the summation of the deflection angle, just to make our job, our work in the field easier. Okay, all right, so that's how it's done in the field. Quite straightforward actually, because it's a simple curve, only one. Already.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.